Hello everyone, in this presentation we are going to discuss about the controller area network protocol. In short, we call it as CAN bus. The CAN, the name itself justifies, it is a network of microcontrollers. Hence it is called as controller area network. Network of microcontrollers means each microcontroller is developing an application and that application is called as embedded system. So it is a network of microcontrollers means network of embedded systems. So CAN protocol in embedded systems. CAN protocol is used to interconnect several microcontrollers. Any application which is developed using microcontroller is an embedded system. Several microcontrollers are interconnected through CAN means several embedded systems are interconnected through CAN bus. Hence, any application developed using CAN is called as distributed embedded system. Example, embedded systems in a car is distributed embedded system. Here you see in this diagram, there is a steer by wire which is a separate embedded system. There is a brake by wire which is a separate embedded system. There is an active suspension which is an embedded system, and there is an engine control unit, that is direct fuel injection system, which is also an embedded system. Electronic throttle level control is an embedded system. Several embedded systems are together, which is meant for giving the convenience, safety and comfortness to the drivers as well as the passengers. Each embedded system is doing a specific tasks, and embedded systems are distributed over the entire car. Hence, embedded systems in a car is distributed embedded systems. So here, much more clarity here. There is a dashboard, there is a lighting systems, air conditioning system, power lock, center locking system, airbag systems, power window and power seats. And similarly, anti-lock braking system, engine control and transmission control and active suspensions are interconnected with the dashboard. So to reduce this complexity in the interconnection between the multiple microcontrollers which is doing multiple job in a car, which is called as ECUs. Several ECUs, which is electronic control units, are interconnected together like this earlier. Because of the presence of CAN bus, it is more comfortable as we see here. So CAN uses bus topology. Because it uses bus topology, several nodes can be interconnected as shown in the figure. This is the CAN bus architecture, and some of the features of CAN bus is being briefed here. There is a multi-master concept. So CAN bus uses multi-master concepts. What is multi-master concept? All the nodes, say for example in this screen, node A is anti-lock braking system and node N is engine management system. So anti-lock braking system is a master, engine management system is a master. Every node is an ECU which is a master. So it is multi-master concept is being used in the CAN bus communication logic. A number of nodes not limited by the protocol, because the nodes which are connected to the CAN bus, so no node addressing, there is no node addressing because message identifier specifies the contents and priority. There is a message identifier. Because of the presence of message identifier, messages will be sent with the corresponding priority. Lower the message ID, higher the priority. So let us look at this in detail soon. So it is easy to connect as well as disconnect of nodes, and it is supporting broadcast and multicasting capability as we see here. And the control area network is an ISO standard of 11898 for a serial communication. The protocol was developed in 1980 by Robert Bosch for automotive applications. Today CAN is widespread in a lot of applications, not only in automobile, in industrial automation, because of its speed, reliability, low cost and flexibility. The CAN standard includes two layers, physical layer and data link layer. In data link layers, all kind of software steps are being involved. As we see here, some of the message types and arbitration rules and fault detection and fault confinement shown. So this is the CAN physical layer structure, which is very clear for all of us. So this is the application like anti-lock braking system application, engine management system applications in the top, as you see here in this screen. And there is an application which is driven by the microcontroller. Here ATC166 is a microcontroller which is driving the anti-lock braking system application. XC167 from Infineon is driving the engine management system applications, for example. Difference between these two is ATC166 do not have on-chip CAN module. So 81C9X is a CAN controller which is separately available, that is communicating with this microcontroller, which does the ABS applications much comfortable. But XC167 have an on-chip CAN protocol. Hence, the XC167 with on-chip CAN protocol is shown here with a yellow and blue color mark inside a single rectangle, which is driving the engine management system. Then there is a CAN transceiver. So on-chip CAN module, then there is a need for CAN transceiver. CAN transceiver will convert the TXD and RXD data into differential data. CAN transceiver will transfer the data from the microcontroller to the CAN bus, as well as CAN bus to the microcontroller, as we see here in this slide. So CAN bus is a differential protocol where CAN high and CAN low are the two differential signal in the CAN bus. CAN transceiver converts the CAN information into CAN high and CAN low, as we see here. So CAN uses twisted pair cable, as we see here, which is terminated with 120 ohm resistance at the ends. Because of twisted pair cable, because of differential logic, high CMRR and noise reduction is more, and the data rate of CAN is about 1 megabits per second, which can transmit the data up to 40 meters at 1 megabits per second. Still you can increase the length, but the data speed will get reduced. That's the only thing. So this is the CAN structure where all the nodes or all the applications can communicate with another application through CAN bus, as shown here, just like that. CAN physical layer logics. So if there is logic 1 means it is called as recessive with respect to CAN. If it is logic 0 means it is called as dominant with respect to CAN. Logic 0 means it is dominant, logic 1 means it is recessive. So all the nodes are interconnected with CAN bus. All the CAN bus uses wired AND logic. Let us say there are 3 nodes A, B and C. There are 3 nodes A, B and C, as seen in the left side of this slide. So if there are 3 nodes means 3 nodes with 3 messages IDs. So let us say 3 IDs means 000, 001, 010, 011, 100, 100, 101, 110 and 111. So when it is 0 means it is called as dominant, when it is 1 means it is called as recessive, because the CAN bus uses wired AND logic. CAN bus uses wired AND logic. What is AND logic? When any one of the input is 0, output is 0. That means any one of the input is dominant, the output is dominant. That is what shown here. Dominant means 0. So except the last row 1 1 1, which is recessive, 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 bus is recessive, bus is idle. In all the other 7 cases, any one of the input bit is 0. Hence the CAN bus is 0, which is called as dominant. That is, bus is occupied. If the bus is 1 means, that means called as recessive, which is bus is idle. Bus is not being used by any of the controller connected to the CAN bus. If the bus is dominant means any one of the controller connected to the CAN bus is utilizing the bus. Something like that we need to understand. The physical layer uses differential transmission on a twisted pair wire terminated with 120 ohms on both sides, as shown here, and the maximum transfer rate of 1 megabits per second at a maximum bus length of 40 meters. When distance increases, the data rate decreases. Nodes are connected to the bus in a wired AND fashion, as discussed. The bus uses non-return to 0 with a bit stuffing technique, which we will be discussing soon. So physical voltage levels and connector. So as we discussed right now, CAN bus is a differential logic which uses CAN high and CAN low. That horizontal line is CAN high voltage level, and the bottom line is called as CAN low voltage level, and the middle bold line is ideal state voltage level. So there are 2 things which we have discussed right now: recessive and dominant. Recessive means logic 1 and dominant means logic 0. In the differential logic with respect to CAN, when the bit is recessive bit from the transmitter, both the CAN high and CAN low bus remains in 2.5 volts. When the transmitting bit is dominant state, the voltage difference between CAN high and CAN low is 2 volts. So default, when there is a recessive bit, both CAN high and CAN low wires will have 2.5 volts, which notifies the CAN bus is transmitting logic 1. When the difference between the CAN high and CAN low is 2 volts, that means CAN high will shift up from 2.5 volts to 3.5 volts. CAN low will shift down from 2.5 volt to 1.5 volts. Okay. So when there is a dominant bit is getting transmitted, CAN high signal will be 3.5 volt and CAN low signal will be 1.5 volt. There will be a 2 voltage difference between CAN high and CAN low for a dominant bit, and there will be 0 voltage difference between CAN high and CAN low for a recessive bit, as we see here very clearly in this diagram. So this is the CAN connector, which is using 9-pin D-type connector, where the CAN low pin is 2nd pin and CAN high pin is 7th pin, and the 3rd pin and the 6th pin are ground pins, and if necessary the power supply to the CAN bus is given through the 9th pin, as we see here. The remaining pins are reserved for future uses. So a recessive bit is represented by both CAN bus lines driven to a level of about 2.5 volts, so that the differential voltage between CAN high and CAN low is around 0 volts. So the recessive bit means difference between CAN high and CAN low is 0 volts. A dominant bit is represented by CAN high going to about 3.5 volts and CAN low going to about 1.5 volts. This results in differential voltage for a dominant bit of about 2 volts. This is what we have discussed right now. And only if all the nodes transmit recessive bits, bus is in the recessive state, as we see here. So all the nodes are transmitting the recessive bits, the bus is also in the recessive state, as we see here. Recessive means pull up state, which is logic 1 state. In CAN terminology, it is called as recessive. When any one of the node sends out logic 0 means what? This will become 1, so transistor will be switched on, and this transistor will be grounding this particular voltage. Due to wired AND logic, bus will become dominant. That we'll see in the next slide. So CAN dominant state, if any one of the node transmits a dominant bit, the bus is in the dominant state. As we see here, node A is sending out a dominant bit which is 0. So the transistor is on because it is inverted. 0 is inverted to 1 because it is 1. So the pull up voltage is dropped to the ground, and the bus has become dominant bus, which is bus has become low. So CAN message format. So the CAN standard defines 4 message types. The first message is CAN data frame. So this is used when a node transmits information to any or all other nodes in this system. And there is a second frame is a remote frame, similar to the data frame without data. And there is an error frame, a special message which is transmitted when a node detects a fault and will cause all other nodes to detect a fault. And there is an overload frame similar to the error frame with regard to the format, and it is transmitted by a node that becomes 2BC. So there are 4 frames: data frame, remote frame, error frame, and overload frame. We will see one by one in detail. So this is the CAN data frame message format. So this CAN data frame format includes several fields starting from start of frame. Always start bits means transition from 1 to 0, start of frame. Then there is an arbitration field of 12 bits. There is an arbitration fields of 12 bits, and there is a control field of 6 bits. There is a control field of 6 bits, and there is a data field of maximum up to 64 bit, and there is a CRC field of 16 bits, and there is an acknowledge field of 2 bits, and then end of frame of 7 bits, and there is an intermission. So this is very important. CAN data frame is more interesting to discuss. So here you see, if several nodes are competing for a bus, and the bus will be given only to the one node, to which node the bus will be given, that is called as arbitration field. So at the end of the arbitration field, the bus will be given to only one node. After that, so it is data length code. Data length code is 4-bit code. When this 4-bit is 1000, 8 bytes are getting transmitted, or 64 bits are getting transmitted in this CAN data frame. If this data length code is 0000, no bit is getting transmitted in this data frame. So length of the data is determined by the CAN data length code in this 4-bit. Say for example, when it is 0001, 1 byte of data will get transmitted. 0010 means 2 bytes of data will get transmitted. When it is 0011 means 3 bytes of data will get transmitted. Data length code decides the length of the data in the data field. So after transmitting the data, we have to ensure that data has been sent correctly without any error. For that, there is an CRC field, which is error detection field, which will help us to ensure that the error-free data has been received. After receiving the error-free data, definitely the receiver need to acknowledge the transmitter through the acknowledgement field. After that, the 7 consecutive logic 1s is an end of frame. Okay, so this is how CAN data will get transmitted from one transmitting node to the several receiver nodes. So first we talk about arbitration field, as we see in this CAN data frame format. After the start of communication, in our example, instead of 11 bits means what? 11-bit message ID. This is called as 11-bit message ID. Message ID means what? This is the message, right? This is the message is going out with this particular identification number. So when this identification number is lower means this message is having highest priority message. Okay, so lower the number, higher the priority. That means lower the message ID, higher the priority for this message. Okay, so instead of 11 bit, the arbitration, how the arbitration is happening, that we will be discussing with 3 bits, right? Assuming that there are 11 bits means 2 power 11, 2048 nodes are connected, 2048 messages with 2048 message IDs are possible. So let us assume all the 2048 nodes with 2048 different messages with 2048 different message IDs are in need to transmit the data simultaneously by using a single CAN bus, but bus has to be given to only one particular node. The remaining 2047 nodes should leave the bus. Among 2048 competing nodes, only one node will catch the bus. The remaining 2047 nodes will leave the bus. This technique of catching the bus with the highest priority message ID and the nodes with the lower priority message IDs should leave the bus. This methodology is called as arbitration logic, bus arbitration logic. Instead of 11 bit, we are going to experiment it with bus arbitration logic with 3 bits. So there are 3 bits means there are 8 possible combinations, assuming that 8 messages with 8 different message IDs like this, because it is 3 bit. Say for example, the first message is having the message ID with 000 coming from one node. The second message is having the message ID as 001 coming from the second node. Third message is coming from the third node with the message ID 010. Similarly, 8th message is coming from the 8th node with the message ID 111. So this 000, 001, 010, 011, 100, 101, 111 is nothing but message IDs. Instead of 11-bit message ID in the CAN data frame format, we are taking an example of 3-bit message IDs as we see here. So 8 nodes are competing for a single bus, and the node with the highest priority message will hold the bus. The node with lower priority messages will leave the bus. How the highest priority node with highest priority message ID is catching the bus, how the node with lower priority messages IDs are leaving the bus, that technique is called as arbitration technique, that we are going to see it now. Let's take the first column, right? At the first column, first node is transmitting 0, MSB bit 0, the second node is transmitting 0, third node is transmitting 0, fourth node is transmitting 0, fifth node, sixth node, seventh node, eighth node, all are transmitting 1. Every node has an intelligence of looking back the transmitted value. This is the more special feature with respect to CAN bus. Every node, what it transmits, it receives the data, and then it can cross check whether the transmitted bit, what we have transmitted, is there in the bus or not, something like that. Okay, what message the node is transmitting, the same bit or the same message, the node can look back and see whether the transmitted message is in the bus or not. So in this context, 0, 0, 0, 0 during the first time, that is t equal to 1. Say for example, I am talking about this particular time. Next to the start bit, the most significant bit will get transmitted by all the nodes, right? All the nodes. In our case, all the 8 nodes are transmitting the bits. First node is transmitting 0, second node is transmitting 0, 8th node is transmitting 1. And as discussed now, all the nodes have the intelligence of looking back the transmitted data. So first node is transmitting 0 and receives the data and checks, okay, I have transmitted 0 and I have received 0, I got the bus. Very happy because it is dominant bit. 0 means dominant, so I got the bus. Second node transmits the data 0 and receives back the 0, and it is happy that I got the bus. The third node transmits 0 and receives back 0, and it says that I am happy, I got the bus. Fourth node transmits 0 and receives 0, got the bus. And the fifth node, this is very important here, fifth node transmits 1 because of wired AND logic. That is, the node is transmitting 1, but because of wired AND logic, the bus is already 0. So this fifth node will receive 0. So fifth node transmitting 1, but it receives 0. Because it transmits 1 and receives 0, it will understand okay, there is some other highest priority message ID node is in need of bus, better we should leave the bus, because when compared to 1 which is dominant, 0 is having highest priority because it transmits 1. The fifth node transmits 1 and it receives back 0. It understands some other node with higher priority message ID need to transmit the highest priority message, better we should leave the bus. Like that, this fifth node will leave the bus because it transmits the recessive bit but it receives back the dominant bit, hence it leaves the bus. Similarly, the sixth node transmits 1 and receives 0, it leaves the bus. Similarly, the seventh node transmits 1 and receives 0, it leaves the bus. Similarly, the eighth node will transmits 1, receives 0, it leaves the bus. So, at the first time, 8 nodes are competing. Out of 8 nodes, due to the arbitration on message priority, the 4 nodes, the 5th node, 6th node, 7th node and 8th node, because all these 4 nodes transmits 1, it receives back 0. These 4 nodes understands that some other node with higher priority message ID is transmitting, hence we should leave the bus. So at the first particular time slot, out of 8 competing nodes, 4 nodes will leave the bus at the first time, something like this. Then at the time t equal to 2, the second bit is getting transmitted from all the nodes. Here there are only 4 nodes are competing for a single bus. So 2 nodes are transmitting 0, other 2 nodes are transmitting 1. The nodes which transmits 0 will receive back 0 and then it feels happy. The node which transmits 1 will receive back 0, and these 2 nodes which transmits 1 will understand that some other node with highest priority message ID is in need of bus, better we should leave the bus, something like that. At t equal to 2, that means the second bit is getting transmitted, means these 2 nodes will leave the bus. Out of 8 competing nodes, in the first bit 4 nodes leave the bus, in the second bit remaining 2 nodes leave the bus, 6 nodes left the bus. There is a competition between only 2 nodes, and the first node transmits 0 and receives back 0. It says, it assumes that I got the bus, but the second node transmits 1 and receives back 0, and it says that okay, some other node is in need of bus because that node is having highest priority, so hence I transmitted 1, I received back 0, so better I should leave the bus. Like that, this node will also leave the bus. Okay, so at the end of the third bit, that means third time, out of 8 competing nodes, 7 nodes will understand that we are sending out the message with the message ID of lowest priority, some other node with the highest priority message ID in need of bus, better we should leave the bus, something like that. All the 7 nodes will leave the bus and only 1 node will catch the bus, and this technique is called as bus arbitration logic. Similar to this 3 bit, all the 11 bits, similar to 3 bits, all the 11 bits will get processed as per similar to this. At the end of the 11th bit, the worst case 2048 nodes are competing for a single bus simultaneously, means at the end of the 11th bit in the identifier field, 2047 nodes will leave the bus because all the 2047 nodes will send 1 and it receives back 0. That understands that some other highest priority node with the message ID is in need of bus, hence they will leave the bus. So at the end of 11th microsecond, say for example 1 bit is 1 microsecond, means at the end of 11th microsecond 2047 nodes will leave the bus, only 1 node will catch the bus. So this is called as bus arbitration logic, and this is called as arbitration field. Next to the startup frame, the competing nodes will understand whom to give the bus based on the arbitration and message priority. One node will catch the bus. Which node will catch the bus? The node with highest priority message ID will catch the bus. All other nodes will leave the bus. After getting the bus, that node will notify how many bytes it is going to transmit through the data length code. If the node is going to transmit 8 bytes with this particular message ID, means in the data length code it will keep 1000 and it will send out 8 bytes, and all the nodes will receive this particular transmitting bytes because all the nodes are capable of receiving back the transmitted bits. So all the nodes will receive these bits, and then after transmitting this 64 bits, then it will check for cyclic redundancy, check for errors. If there is no error, So the received node will acknowledge through the acknowledgement slot, and then the end of frame will happen. So this is fantastic. So there is something like remote frame message. Remote frame is similar to the data frame without the data field. That is shown here clearly. Remote frame is similar to the data frame without data field. So it has start bit, arbitration field, data length code, CRC, and acknowledgement and end of frame. Only it does not have any data field. That is the one we need to understand. That is what your remote frame. And the error frame is if there is any error in the arbitration, if there is any error in the data length, if there is any error in the data, if there is any error in the CRC, the nodes will notify the bus through an error frame message, something like as shown here. So error flag field and error delimiter field through the 6 to 12 bits, it will inform the bus that the error there is an error in the bus. So all the transmitter and receiver will understand the data has some error. Transmitter receiver will discard the corresponding messages, and the transmitter will understand I have to retransmit this particular data once again, something like that. And if the node is too busy and then node want some more time to do some other work, it can send the overload frame and request all other nodes not to transmit the data for a while through by sending the overload frame message, as we see here in the screen. So overload frame is also 6 flags and then 0 to 6 flags of 0 and then 8 error delimiter of recessive bits as shown here. This is called as overload frame. And there is something like interframe space between one candidate data frame to another candidate data frame. There should be an interframe space of approximately around 3 bits, as we see here. And this is what very clearly mentioned. There are two versions of CAN bus, which is CAN version 2.0A and version 2.0B. So 2.0A and 2.0B is differentiated with the message identifier as shown in the yellow color. So 2.0A uses 11-bit message identifier. 2.0B uses 29-bit message identifier. That is the only thing. That is the only difference. Rest of the thing remains same for 2.0A and 2.0B. B means 29-bit identifier. A means 11-bit identifier. In the I2C protocol, every node will have an ID, but here every message will have an ID. So node is not bothered in the CAN bus. With respect to our discussion, let us look at some benchmarking Texas Instruments, what they are telling about CAN protocol. Let us look at it, which will be more comfortable for all of us. So as discussed, CAN uses physical layer, data link layer and application layer. So in the application layer, all our microcontroller is sitting. In the data link layer, our microcontrollers are sitting. In the physical layer, the connectors and the CAN transceivers are available, as we see here. So this is the CAN bus and the CAN transceiver connected with the CAN controller, then to the corresponding digital signal processor or microcontroller. Okay, so out of 7 layers, CAN bus uses 3 layers: physical layer, data link layer and application layer. And this is the CAN data frame format as discussed right now. It has a start of frame, 11-bit identifier and remote transmit request, identifier extension, because CAN 2A and CAN 2B is there now. So whether it is 11-bit identifier or 29-bit identifier is notified through the identifier extension bit in the CAN data frame format, and followed by data length code and 0 to 8 bytes of data and CRC, then acknowledgement and end of frame and interframes in space. That is what we have discussed, a rough 11-bit identifier, and similarly 29-bit identifier. So 11-bit plus the remaining 8-bit identification is 29-bit identifier, and the remaining things remain same: data length code, 0 to 8 bytes of data, CRC and acknowledgement field in CAN 2B. That is what with respect to this. As discussed, the arbitration on message priority as told. No? So here, as we see here, what is getting transmitted, the node is capable of receiving back and see what is being transmitted. So as told, if it is recessive bits, both are in 2.5 volts. If it is dominant bits, CAN high and CAN low is differentiated with 2 volts. Default it remains in 2.5 volts. That is shown here very clearly. Texas Instruments also, with Texas Instruments content also, we are cross checking and we are understanding this. So the CAN bus is to differential bus which has CAN high and CAN low, terminated with 120 ohm resistance, which has a CAN transceiver and CAN controller, all are connected to the bus topology. Okay, so bus topology is being this. If it is a network, means how they are interconnected, we need to understand through the topology. So here CAN bus uses bus topology as we see it. So in the CRO, we are able to see the transmitting data and the CAN bus data and then received data. The transmitter sends out the recessive bit, CAN bus remains in 2.5 volts. If the transmitter sends a dominant bit, the CAN bus will have CAN high and CAN low with difference of 2 volts. CAN high is around 3.5 volts and CAN low is around 1.5 volts, where the difference between CAN high and CAN low is 2 volts. So during dominant bit, CAN bus will have a differential voltage of 2 volts. During recessive bit, both the CAN high and CAN low will remain in 2.5 volts, and the received data is the same. The receiver output receives from this through the CAN transceiver. Okay, so very clearly Texas Instruments data is also telling the same thing. So what Microchip says about CAN. So introduction to CAN. So what they used to say, CAN protocol, what is CAN, its characteristics, message frame, error handling, CAN in action, and summary and references. What do they say? They also saying the same. CAN stands for Controller Area Network and is defined in ISO 11898. Its key characteristics are: CAN is an extremely robust serial communication protocol, message based, not address based. Message ID, as we discussed, distributing control across the CAN network that allows peer-to-peer or master-to-slave style of communications. So CAN uses 3 layers: physical layer, data link layer, and the application layer. So in the physical layer, it talks about medium dependent interface, physical medium attachment, and physical signaling, where bit encoding, decoding, and bit timing and synchronizations are there. In the data link layer, there is a logical link control and medium access control. So data encapsulation, decapsulation, frame coding, error detection and signaling, serialization, deserialization are taken care by the medium access control. Acceptance filtering, overload notification, and recovery management is taken care by the logical link control according to ISO 11896-1 standard with respect to CAN. And the physical network, as we see, it's CAN high and CAN low with the terminator 120 ohm resistance, and there are a dashboard node and an engine node, and there is a door node, all are interconnected together as we see here according to the CAN bus standards. And as we know very well, there is a separate microcontroller, and there is a separate CAN module, and there is a separate CAN transceiver which is connected to the CAN bus. Or there are microcontrollers which has on-chip CAN module. So the microcontroller along with the CAN module can be interconnected to the transceiver like this. And there is something like CAN IO expander also, which can be connected to the CAN bus through a CAN transceiver, which is very interesting. Different types of nodes can be connected to the CAN bus as shown here, which is much more comfortable for us to understand. As we know very well, there are data frame, remote frame, error frame, and overload frame. The same thing you are going to refresh once again. So 11-bit identifier CAN 2A, where you can see the arbitration field is 11-bit. 29 identifier, which is extended identifier, so 29-bit identifier. Okay, it's very interesting, right? So there is a start of frame, arbitration field, control field, data field, CRC field, acknowledgement field, and end of frame, as like we have discussed. So arbitration field 11-bit, where the multiple nodes fighting for a single bus will get convinced, that is arbitration and message priority. After that, the data length code, this 4-bit DLC 0 to DLC 3 will choose how many bytes are there in the CAN data field. If it is 1000, 8 bytes are there in the data field, which is 64 bits. After 64 bits are transmitted, there is a 15-bit CRC with CRC delimiter. After checking the error, the received device will acknowledge the transmitter that by pulling down, as like I2C logic. Here also, the received device will pull down. That means it will make the acknowledgement bit as dominant bit, where the transmitter will understand the transmitted data is received correctly by the receiver. And 7 consecutive ones are end of frame. 7 ones, 1, 2, 3, 4, 5, 6, 7 ones are nothing but end of frame with respect to CAN data frame format with respect to CAN bus. And the remote data frame, if some node wants to read the message from this message ID, means it can send the remote transmit request. So from which message ID the node is requesting. So next to the start bit, that message ID, 11-bit message ID, then the RTR bit will become recessive. In the data frame, the remote transmit request bit is logic 0, which is dominant, but the remote transmit request bit is recessive in the remote frame. That is the only difference. Then the error frame, there is an active error frame and passive error frame. Active error frame will have a 6 plus 6 consecutive zeros followed by 8 ones, but the passive error frame will have a 6 plus 6 12 consecutive ones with again another 8 consecutive ones. So when there are more than 7 ones means that itself is an error. Okay, so that we need to understand. So there is an active error frame and passive error frame, and there is an overload frame with 12 consecutive zeros and 8 consecutive ones to make the transmitting node to wait for some time. And this is very important to focus now. Carrier sense multiple access and collision detection with collision resolution. What do you mean by carrier sense? Every node must monitor the bus for a period of no activity before sending message. So carrier sense. Carrier means what? Bus is a carrier. So every node can sense the bus. Carrier sense means every node must monitor the bus for a period of no activity before sending the message. Multiple access means what? Once a period of no activity occurs, every node has an equal opportunity to transmit a message. As like bus arbitration, right? All node will keep the arbitration bit in the bus, and based on the priority, one node will catch the bus. But all node will have an access to the bus. That's what multiple access. All the node can sense the carrier, all the node can access the bus. That is carrier sense multiple access. Then collision detection, if two nodes transmit at the same time, then collision occurs. That is what collision detection. And collision resolution, in our case it is a collision resolution, non-destructive bitwise arbitration. That is what we did right now, right? What we did was non-destructive bitwise arbitration. Messages remains intact even after the collision occurs. So collision means what? One node transmits 1, another node transmits 0, means the node which transmits 1 will receive back 0. That means node which transmits the recessive bits will receive back dominant bit if some other node sends the dominant bit. Means this is called as collision, but it is needed in the arbitration field as per our discussion. It's very clear. So CSMA bar CD and the carrier resolution, how it is being done means there are two nodes, node 1 and node 2. Node 1 is transmitting recessive and node 2 is transmitting dominant bits. Hence node 1 leaves the bus and node 2 catches the bus and keep on transmitting, and node 1 keep on receiving the bus. So node 1 is not transmitting anything, node 1 receives something, node 2 transmits and node 2 receives back. Every node which transmits is capable of receiving the data, and all the nodes are connected to the CAN bus. All the nodes will receive. Say for example, node 1 is also receiving the node information which is transmitted from the node 2. As we see here, it's very interesting. So initially in the node 1 is transmitting, node 1 is in need of bus, node 2 is in need of bus. Next to the start of frame, both the nodes are transmitting the message IDs. Node 1 is transmitting the recessive message ID, node 2 is transmitting the dominant message ID. So node 2 will catch the bus, node 1 has lost the bus. That's what. Transmitted recessive but detected a dominant. So it transmits the recessive bit but it detects the dominant bit. But it transmits the dominant bit, it detects the dominant bit. Hence transmitted a dominant, detected a dominant. Transmitted a recessive, detected a dominant. So last arbitration, node A leaves the bus, node B catches the bus because node B transmits the message with the highest priority message ID. Hence node B communicates and node A receives. That's very interesting. So this row is transmitting message, this row is receiving message of node 1, this row is transmitting message, this row is receiving message of node 2. Where node 2 transmits and receives, node 1 listens because node 2 wins the arbitration. It's very clearly mentioned. It's discussed. Okay, synchronization is to the clock based synchronization, and there is something like bit stuffing, right? 7 consecutive ones means it is end of frame. So there should not be 7 consecutive ones or 7 consecutive zeros. If so, the nodes will misunderstand that as a end of frame. So whenever there are 5 consecutive ones or 5 consecutive zeros, its opposite bit need to be stuffed, which is called as bit stuffing. Here in this case there are 7 consecutive zeros. 1 2 3 4 5 6 7 consecutive zeros. So at the end of the fifth consecutive zero, one bit of logic 1 is stuffed. So this is mandatory. This is called as bit stuffing. That is, stuffed bit occurs after 5 like bits in a row, either recessive or dominant. Okay, so here there are more than 5 consecutive ones. So next to the 5 logic ones, a 0 is stuffed in between more than 5 consecutive ones. So when you are transmitting the CAN message from the node, this is the procedure. Transmit the data with the message ID. That is message ID, first the message ID, then the number of data length code and the corresponding data bit alone we have to transmit. Then the CAN protocol engine will do start of frame, it will add the CRC bit, it will do the error checking bit, and it will look at the message arbitration part, and then it sends out to the CAN transceiver. So when a CAN node is transmitting, bits means transmitting byte 0 and transmitting byte 1, etc. means, so message ID, data length code and data. These three which we need to concentrate while transmitting a data through the CAN bus. While receiving, the receiving is very interesting, right? So from the CAN bus through CAN transceiver, it will receive the CAN data. So we have to do the bits destuffing of bits, and we have to check for errors, and we have to acknowledge, and we have to look at all the data. And then there is something like message assembly buffer. All the messages are consolidated in the buffer, and then there is a filtering, because all the nodes will receive the messages. Which message with which message ID is needed, that alone filtered out in the receiver, and then the receiver will take the corresponding data along with the data length code with the corresponding message ID. If the message is not for this particular node, the filter will filter out, the node will never receive the message. So every receiver will have a arbitration, that is message filters. Okay, so those filters will filter out the unwanted message. So the filtering is based on message ID. That's all. Filtering is based on message ID, that we need to understand. So that's all about the microchip point of view with respect to CAN bus. LPC2129 is an on-chip CAN module, something like this as you see here, which has a 2 CAN transmit data, receive data, CAN transmit data and receive data, as we see here. So these are all the few references.